All right, let me make sure this is lined up. Hopefully this is recording again. The board appeared back up. So we've now had maybe a 10-minute break or something. So we'll pick up on here and going. So we're trying to induce this one to be a 0. The way in which he does it is by taking these little multipliers that's going in. So against this A, we're going to multiply an L times A to generate U. That's what's going on. So we're never going to actually record L. We're actually going to just do the effect on A to get the U. Because if you remember, I don't really care about L. I just need to be able to convert this situation to get them. So what I really need is the L inverse times B and L inverse times A. Because this is L inverse times A and this is L inverse times B. So if I put L inverse here times A, so what we're going to actually do is figure out this L inverse times A. And he does it very simply. Well, the trick on this is by taking a simple form. Imagine I have an L that looks kind of like this. This is a lower triangular matrix, right? And its inverse is just itself. Now, imagine I had an A here. What would have to change here to make that work? Well, what you want is you want L times L inverse to be equal to identity, and L inverse times L to be equal to identity, and you want them to be symmetric. So there's some basic requirements that go into it. I'm not going to worry, these are called the Moore-Penrose pseudo-inverse conditions. And if you meet those conditions and your matrix is invertible, then it's a true inverse. All right, I don't want to get into like, because I think I cover all that inside the video, so I'll double check. But I believe all that's covered in there, so I don't want to waste time here on it. It's not really a waste, but it's... So essentially I'm going to worry about this condition, which means I want to find out what I need to do here. So I can use A, letter B, C, D, E. Now, I can just walk through and I've got 4 unknowns, but I got 4 equations, one for each element here. Now, if you walk through here, what you'll notice, now there's 2 ways you could do it. You could walk through and figure out what these are by writing every equation out and solving. There's a second one, which is I could go in and I could submit to you a candidate solution, and then you could verify that solution is correct. Now this always bugged me as a technique, because I'm like, it's like magic, guess and check that's going on. So I'm going to violate my whole thing on here, because I am going to give you a magic solution, guess and check. But I'm not going to tell you why this is so important. Because it turns out that while this gives me an easier way to, it's kind of quicker to check here, it turns out for an awful lot of problems out there that this allows me to do things I can't do the other way. So this right here, what I just did, is a fundamental statement that it's easier to go this way is basically P versus NP. Right? That should take you aback for a sec. But the whole situation is when we write an algorithm, typical polynomial type algorithm, what I do is I start from first principles and I build, I construct. So it's a constructivist argument. I start from these first things and I walk my way out. Right? And under those situations, we don't know a polynomial algorithm for these standard kind of deterministic Turing machines. We don't know an algorithm that will solve these NP problems. Right? That's different from saying one doesn't exist, but nobody has ever found one. Right? And that's the P versus NP problem. Is there a deterministic Turing machine solution, this nice constructivist thing, that will generate the solution? None has ever been found, doesn't mean it doesn't exist, but it kind of starts to indicate this is less likely. Right? This technique is, I guess a solution and I can check it very fast. Right? That's what a non-deterministic Turing machine does. Now, we don't know how to build one. People make charges saying, hey, maybe that a quantum machine is a non-deterministic Turing machine, or this, that, or the other. Right? There's lots of candidates that are out there. I submit to you that there is a known way to build a non-deterministic Turing machine. And it's called humans. We know how to make more of them, right? But think about how people solve things, right? Have you ever had intuition? Well, what's intuition? You've got a good idea of what the solution is, and then you check to see if it's right. You do what a non-deterministic Turing machine does, and it works really well, actually, right? So this technique of kind of getting an insight out of the blue that's coming in and then checking to see if it works is a fundamental human technique that is different from the constructivist and turns out to actually have a lot of things. Sometimes we really do just get an idea out of the blue and we don't know how we got it. Now sometimes we do, and the way we got it was really convoluted, confusing, and it's not helpful to show you that technique. Okay? I submit to you this is that second form. I told you the way you could get on your own, but I submit to you that it really is not helpful to actually plow through that algebra. It's much easier to check here. And the idea of getting a good idea and seeing if it works is really, really helpful. An awful lot of really good computer algorithms have been generated that way. So they had a screwbally idea, they checked and it worked. Right? And originally they didn't have a full proof, but darn it, they came up with one later. Okay? So I don't want you to blow out your intuition because it doesn't seem under the scientific paradigm. It really is, right? Guess and check. I mean, that's entirely what human science is all about. So this is why it kind of carries into this areas. So, right, when we're doing it, you can come in. So when we're doing that, this is kind of the submitted area that's on it. If you check it, right, this first one, since there's a 0 here, right, you get 1 times 1, 0 times 0, so you get 1. Right? Here, the 0 hits there, the 1 hits on that 0, so they just cancel out. That gives you the upper. When you go to the next row, you get A minus A. Gives you 0 on the lower. And then when you do the last, the 0 hits the A and the 1, so it gives you 1. So it nicely does give you the inverse. You can try it the other direction, right? But you can easily just notice by negating these, it doesn't change anything. So you've shown it works both directions. Now, this is where it works out. So that means it's actually really easy to get the inverse. Now, I don't actually ever need to store this. The other nice thing is, it's the 1 on the main diagonal means I'm keeping them in the order they're at. And then all I'm doing is doing something below the diagonal to take combinations of the first one and subtract it, because I'm using the inverse to carry it on. Now, I need L inverse times A to get U, and I need L inverse times B to give me my Z. Because back substitution takes this equation and gives me L inverse B equals Z. So back substitution is just a fancy way of inverting a diagonal matrix. So what Gauss has is Gauss in essence has a particularly nice form of this, where it's very easy to write what that inverse looks like. So that's why this is really cool, is because it's easy to get that. And that's why I said this first step can really kind of go away, because I can do this. Right? That's all you want. But in order to do this really easy, I don't have to do 2 separate equations. I just do A, B, and call it a new matrix. When I multiply it by L inverse, that'll give me L inverse A and L inverse B. So all I have to do, this is called augmented. All that means is when you're solving this thing, I don't need to do them separate. I just stick B in there, and I just pull the last column out. So it turns out to be easy. So this whole step just drops into here. So I don't actually have to do this one. It saves time, and it's also, believe it or not, saves a lot of numeric precision. Because remember, that substitution thing has the ability to build error. So you would have done this same L inverse to calculate it, and then you would have compounded the error when you did the forward substitution. Whereas if I do it this way, it just happens once. So the error doesn't build. So that gives me kind of a nice thing all at once. So it ends up being faster, taking less memory, and also reducing errors. That's kind of rare. When all of those things work out, all you can say is not that that, you know, this is a kind of a better word, or that these are equivalent things. It turns out that this is just the dumb way to do it if you actually do the forward substitution. And this is the smart way. Not everything is a dumb versus smart, right? Gaussian elimination versus QR factorization is a choice. QR is more stable, Gaussian elimination is faster. That's a trade-off. So it's not a choice of a good method versus a bad method, it's a choice of which is the appropriate method that's going on. Right? So you're picking between two good methods and you're just seeing which good method fits better. Right? If you actually implement this in what appears to be the obvious way, the easy way to prove, you're actually doing the naive thing, and the naive thing ends up just being bad all around. It's slow, it takes up memory, and it's error prone. Right? When there's no good feature of something, we just want to eliminate it. All right. So that's my soapbox for the day. All right. So it makes sense kind of what's going on here. What we're going to do is worrying about, therefore, how to just get these. And the reason why I only have to worry about those is because the rest of it's pretty obvious. Right? And since I'm going to apply it to everything all at once, I don't need to store them. So I'll just throw them away when they're done because I'm going to get what I want by applying it to the matrix. So that makes it very memory efficient. So I submit to you now, all I have to do, if I show you how to do it on A, it's trivial to extend it to AB, because just make AB and submit it as your new A matrix and you're done. Right. So, I want to induce this to be 0. Well, that's pretty easy. What I want to do is, to this particular element, I want to add in combinations of this element here. So that means I need to take this element and I have to multiply it by, I need this to become A21 with a negative sign. So if I multiply it by A21 over A11, right? A2 minus A21 over A11 times A11 gives me minus A21. I add it to that row. This becomes 0. This is going to become something else. Right? This one, by that diagonal, is just going to stay the same. Right? But when I do this matrix, top row gets preserved. Therefore, the smart thing to do is don't actually multiply by 1. Just leave it. Right? Just deal with the smaller and smaller matrix as you walk through. And then this one is going to become A21 minus A21. So I'm going to write this as plus a minus. Because that's just the coefficient. Times A11. And then, give myself enough room here. And I've got A22 plus minus A21, A11. So we're just taking what was there plus this coefficient times the element above. If I had multiple rows, I would have different top elements. It would be whatever's the first one. The whole reason you want to pivot is just to make sure whatever's getting pulled in, the A11 is the biggest, because if I divide by a big thing, this becomes small, so the update is small, so the error is small. So if you force this to become the biggest one out of all of these, it'll be best. And then whatever's left over, I want the biggest one in the next diagonal row, and so on down the line. That's going on. Now, this being said, right, this is that next step. But what is this? Well, darn well better be 0, right? Right? A21, right, plus a minus A21 divided by A11 times A11. Well, this should cancel this, so I should get A21 minus A21 should be equal to 0. Mathematically, it's 0, right? So if you calculate this, this will always be 0, right? No, it'll never be 0. Well, I shouldn't say never. It'll almost never be 0 on any computer. Because computers, when they calculate this, don't have infinite precision. And even if they had infinite precision, when you measured it and entered it, you probably did something wrong. You probably measured it wrong, errors built in, all kinds of junk like that. So what happens is, this is almost never zero, but it should be zero. If you are therefore smart, you don't calculate this, which this is work to calculate it, you just make it zero. Or you could really be lazy and just not do it at all. And then when you do your back substitution, you're never looking at that element anyway. So this sounds really lazy, but in reality, most really good computer programs never actually touch this element at all. You just know when you get back, there'll be garbage there, it'll be what was originally in the matrix. But since your substitution algorithm, back substitution, should never look at that entry, if you write it correctly, why should I bother to take the time to calculate an entry you're never going to look at? Right? So if you write your back substitution correct, it never accesses this, so I can now write this so that I never touch it. I never touch it other than to get that element. And then I'm done. It turns out if you do that, again, it's faster, it's better memory, all kinds of other lovely stuff that goes on. You've improved things. So these, I'm trying to mention these because these are the little tunes that go into what makes a really good algorithm to take care of it. You look at it, what do I really need for the next step? Right? And this is why I say you want to be careful because, you know, if you just look at the basic algorithm, you would think that's going to be a zero. So a lot of people just write a simple one that just multiplies the whole thing. Waste time and it's inefficient. So, you know, this is the idea of what Gaussian elimination is about, and this is the parts that matter when you write an algorithm. So hopefully this makes sense. Really what you're getting is, at the end of this, you just care about the U, right? And the L inverse times B. So that's why most good ones of these things will give you, you know, a Gaussian elimination algorithm where you pass it an augmented A, and it'll pass you back a U. And then the last column of U is your L inverse times B, and you pull that one out and you stuck the B in the first place. And then you get everything, and then you just take that and work off it. Right. Reduces memory requirements, all kinds of lovely stuff. It turns out the nice thing about Gaussian elimination is this is actually fairly decent for sparse matrices too. As long as you implement the pivoting. If you don't do pivoting, it can get really ugly really fast because you can end up with zero on the diagonal. And I think one of the practice labs actually demonstrates that. What's going on. I think the way I wrote it was such that it would force you to end up with zeros on the main diagonal so that you would have to pivot, otherwise it blows up in your face. All right, so this still has back substitution and some other things that are in there. So this is where we come into some other things. This L that I was doing, L can also have some errors that can creep into it based on what the scaling is that we just talked. Right? If you don't do the pivoting, it can get kind of ugly. Instead of doing this, I could take this and I could take A as QR. R is an upper triangular matrix, so I can do back substitution. Q is orthogonal. So the neat feature about this one is since this is orthogonal, it's like multiplying by 1. It's the closest thing to multiplying by 1 in matrix land. So when you multiply by this, you get, you get a number of nice things. For instance, Q inverse is Q transpose. Right? If you go into complex, this just becomes the Hermitian transpose, but I'm not going to worry about that. This gives me this nice orthogonality condition that goes on. That's very easy to calculate. But the nice thing also on this is since I have that my Q transpose Q equals I, this is the norm of Q. Right? This is just a direct carry of that statement, right? Since Q inverse is transpose, this is Q inverse times Q, which is the identity. But this means the norm of Q squared is the norm of I, which is 1. So the norm of Q is 1. Since the norm is 1, that's the scaling factor. The ratio of your largest to your smallest singular value gives you your condition number. Well, in this case, your largest and your smallest values are 1. So the ability for errors to grow on this is not. Whatever size error you get, that's the size error you get out for Q. So when you're doing this initial reduction to the upper triangular, what you end up with is this step, by doing a Q instead of an L, cannot cause errors to grow. They'll be proportional to whatever size you started with, which means your only errors are here. So that's significantly reduced your errors that's going into it. Now the only thing better than this is I still get errors on the backside. So it would be really nice if I could take and have two orthogonal transforms, one on each side, that's going on. This is what's called the singular value decomposition. Right? So this one, I'm not going to go into how do we do this, because there's a lecture online that does this, and then in the fall, we're actually going to take a look at trade-off of 3 different versions of this. So, you know, look at the householder, how householder QR is done, because that one always throws people. You'll want to see it a second time in the fall again, because it's just one of those ones that you have to see it a couple times for it really to clarify. But that'll kind of cover where this one goes. This is the 10,000 foot level of what's going on. The other thing that goes in, and this one is the SVD, singular value decomposition. What it does is it decomposes this and this are orthogonal matrices. So again, like multiplying by 1. So there's no error here. This is diagonal. Remember, diagonal is completely independent, nothing grows. So in this case, I've got 2 different things. So I can solve this the same way. You know, I just end up with B equals U sigma V transpose times X. This is my A. This is just B equals AX. But now all I have to do is multiply by U transpose, knocks this out. This is diagonal, so I can independently solve each one with the scaling factors. I multiply both sides by V transpose, or sorry, by V, and you have your solution. And at no step along here, the only one that can cause any errors is this scaling that's here, but each one's independent, so the errors cannot build. So that's why we like this one. It's as safe as you can ever solve this problem that's going on. So why don't I always do this? It's slow. That's why. Slow, 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 and it takes a decent amount of memory, because calculating these orthogonal matrices is where the problem comes in. And we will talk about actually how you can get some of these, again, in the fall. So that's where this ties into where the fall goes on. So we'll hit this one, and then we can use that one to actually get this. That's going on. But that becomes kind of fundamental. So if you're willing to spend more time, more memory, more everything else to get it, I can make it more and more stable. As your problem gets uglier, I spend more work, I can fix it. Right? But if it's not unstable, why spend the work? Go to the fast, easy one. So now it's kind of a work continuum, right? Where you say, how bad is it? If it's really easy, do the easy thing. Right? If it's a little bit tougher, do the little tougher thing, but don't go any further than that. Why do more work? If it gets really ugly, you go here. If it gets beyond ugly, and it won't be solved here, use a completely different formulation. That's why we said there's multiple different ways that we can solve them. Then that means this is the wrong way to formulate it. If it gets too ugly in this, AX equals B way, I can almost guarantee there is some other way out there where it will be easy. So do it the easy way. Make sense? All right, so this is kind of my 10,000 foot overview of AX equals B that's going on. Please do take advantage. I talk about projection methods and all kinds of stuff like that in the online lectures that are recorded and up there, and getting into householder. Please take a look at those, try some problems. Thank you all.